Any questions? You'll be excited. What's the last thing we did?
We're talking about how centripetal tension, pulling it towards the center.
Okay.
And
So I'm done with slinging the thing around my head.
Yes.
So you're driving a car and you're taking a curve. What affects how easily the car can take the curve? And if you have driven when the car has skidded a little bit, that would be probably very helpful to answer the question. What would cause a car to skid going around a curve?
Going too fast.
Okay.
Less friction.
Pardon?
Less friction.
Okay, I would lump that in with going too fast for conditions.
Okay.
That would combine those two.
How sharp the turn is?
And that's the other key thing. I was about to say, if I'm going 60 miles per hour in a neighborhood and take a right turn, that's probably gonna be too fast. If I'm on the highway and I've got a nice lazy turn, probably not gonna be an issue. So as the using the physics term, the radius of curvature, the tighter it is. So if I've got a turn like that and a turn like that, what you would do is draw a dotted line perpendicular to the curve, draw a line perpendicular to the curve, and that distance right there would be the radius of curvature. Here, it's a much tighter curve. And so it's a smaller radius of curvature. So how tight the turn is, it's a small radius. So as the radius gets smaller, is it harder or easier?
Harder.
So if we were looking at the force it takes to keep you in that curve, it gets harder. You need more force to keep you in that curve if it's a tight radius. And put a little r on the bottom there. So as r gets smaller, the force required gets bigger. With any fraction, any positive fraction, as the denominator gets smaller, the whole thing gets bigger. What about speed?
You have to go slower or less speed.
To take the curve. Okay, so as speed goes up, it gets harder to maintain that curve, and so it goes to the top, and then it actually is squared there. What I'm getting to is that right there is the formula for centripetal acceleration. As you saw in the lab last week. I think you did centripetal. Yeah, that was last one.
Yeah.
Thursday. I'm about to write it up more formally. This is just for the purists in the group. I know the centripetal acceleration is pointing towards the center. The centripetal force is pointing towards the center. But how do you convey towards the center without having to write out towards the center? Because that's way too much writing. How do you generally indicate direction?
Positive or negative? No.
If it's a one-dimensional problem, yeah, you can get away with that. But if it's a two-dimensional problem, how do you indicate directions?
I had J hat.
But with I hat, J hat, we got this nice, math coordinate system. I hat, J hat, or I hat, J hat, or however you're going to do it, but they're perpendicular to each other. But now we're not really pointing in one direction, we're pointing away. We need to somehow indicate away from the center or toward the center. introduce to you the radial unit vector. R hat. I hat is points in the direction that you say it is, J hat's perpendicular to that, pointing in the direction you say it is. R hat's got slightly different restrictions on it. R hat points away from the center. The only thing you're deciding is what's the center. So R hat, unit vector, that's the hat. Unit vector. Pointing away from the center.
You said J hat was the perpendicular
The I hat.
to I hat.
Officially, you could use a unit system where they're not perpendicular to each other. However, I would not recommend that until you get into the graduate level physics.
Okay.
So if R hat is a unit vector pointing away from the center, but centripetal means pointing towards the center, how would I indicate that? This is away, how do I do towards? Just draw an arrow. Is that what you're?
From, away from?
I
From
missed
the
it.
center, away from the center? No,
I heard away from.
like away and then from?
Oh. I was saying actually write out the word from or away. No, that's too much writing for us. Yes. The way we generally indicate, the other way is a negative.
A negative.
So R hat is a unit vector pointing away from the center, negative R hat, unit vector pointing toward the center. And so officially, we would write this as centripetal acceleration is equal to and you stick the negative up front, out of v squared over r. So the direction is the negative up front combined with the r hat at the end.
And that's towards.
Yes, that means toward the center. And so centripetal force would be mass times the centripetal acceleration, which would be, just stick an m in front of that, negative m, v squared over r hat. Now, the actual notation is not critically important. The big takeaway is that recognizing centripetal forces towards the center. Despite the way you might feel when when you're driving a car and going around a curve. Because if I am in a car going around a curve, think about what your body wants to do. I think I did my Godfather 3 line in here. Where's my other group? Is this, okay. So if you're in a car going around a curve like that, at this point, your body, if you're driving, your body wants to go straight. The car is curving. You are not being thrown outwards. Your body wants to go in a straight line. It just feels like you're being thrown outwards. Yes?
You said that the one with the negative, v squared, that's, towards?
This is centripetal acceleration and centripetal force, where you just stick an M in front. Does that answer your question?
Yes.
Okay. So let's combine a couple things. Earth. Satellite. Satellite's going around Earth. Excuse me. All right, start out, force diagram of the forces acting on the satellite. Anything we can get rid of?
Other.
Yep.
Tension.
I would assume.
Oh, wait.
You nailed it at the wrong time. All right. Somebody else said something else while I was coughing.
Weight.
Now,
Is there no weight due to gravity or?
there is a force due to gravity,
Okay.
because all you need is two masses. So I'm gonna keep that around. It's not really called weight anymore, but this W stands for weight or the generalized gravitation. Unless you wanna go to F-tong instead of F-town. What about friction or normal force?
No friction.
Yeah, normal force? What is the requirement for normal force?
Has to be perpendicular, right? Something has to be perpendicular to something?
Okay, but let's narrow that down. Normal does mean perpendicular. What is the requirement?
Two masses touching.
Again, in unison?
Two masses touching.
Oh, mass is touching. Yeah, it has to touch something. So what is the satellite touching?
Nothing.
Nothing. So normal force is gone. Friction also requires touching. So all we're left with is this gravitational force. So if we did the force diagram, they're already separated from each other. It's not a particularly exciting one. I'm gonna write F sub G instead of W, because we are talking about the generalized gravitational force. Since if it's a satellite, it's probably not particularly close to the surface of the Earth. So if I plugged in that F equals ma, I've got one force acting on it. So I'm plugging in that F equals ma. The force is the force due to gravity. My acceleration is, well, I have something traveling in a circle. What do we call that acceleration? Somebody say it loud and proud.
Say what?
What type of acceleration for something traveling in a circle? What is it called?
Centrifugal acceleration.
Is that loud and proud?
I don't know how to say it.
Okay.
Centrifugal.
Centripetal or centripetal, either one. Centripetal acceleration. I know the force due to gravity and the centripetal acceleration are both towards the center. So this is the mass of the satellite. So I know on the right-hand side, I got mass of the satellite times v squared over r. Question, what goes on the left-hand side? What is the formula for the generalized gravitational force? I don't think we've done that before. If we know little g, we could do that, but we don't know little g. If I wrote it down, I would have written it down when we did potential energy formulas. All right, let's
Is it
think through it.
FG?
Oh, somebody just get it?
Is it the FG, I mean the minus GMI M2 over R plus C?
That is the gravitational potential energy, not the force. All right, so let's think about it. Gravitational force. What do you think affects it?
Two objects.
Okay, got two objects. What about the two objects would affect it?
Their, not their weight. No.
Not their weight.
Or mass.
What was the last thing?
Mass. No,
That does depend on the mass.
it does.
Yeah, I mean, if I ask you, weight is a gravitational force. So gravitational force has to depend upon at least one of the masses. Matter of fact, from a physics point of view, there's nothing is absolutely still. In other words, I got this force due to gravity acting on both objects. It shouldn't matter which object, if I could do it from the point of view of the satellite or the point of view from the Earth. Both masses need to have some importance there. And also, since that gravitational force is the same between the two objects, I should be able to just change my point of view and get the same answer. What I'm heading towards is that whatever I have to do with these masses, I should be able to switch the order of it and get the exact same result. Well, what are the two math operations where I can just switch the order and get the exact same result?
Addition and multiplication.
Those are the two. In this case, it happens to be multiplication. Magnitude. So I got two masses that are multiplying together. It is similar to the electric gravitational potential energy, not electric, gravitational potential energy formula, but there are some differences. All right, what else do you think affects the gravitational pull? Or why aren't we using mg? mg. And not having heard the question, Leslie's about to tell us the answer. Go.
What was the question?
You were supposed to just randomly throw out something, and if you got it right, that would have been incredible. You want to randomly throw something out?
Number 5?
I appreciate your trying. And the question is, we're trying to figure out what affects gravitational force. And we've established at this point, both masses matter, the product of the masses.
The velocity of the,
The speed of the object is actually not going to affect it.
okay.
The distance?
Yes. The distance. So, the farther out you go, stronger force or weaker force?
Stronger.
So the farther you get from Earth, the greater it pulls you back in?
No.
The weaker. So the farther out you get, the weaker the force is. It's one of those two. What's your gut tell you?
It gets stronger.
Like a rubber band. The more you stretch it out, the greater the force.
Well, no, it gets weaker because then once you let it go,
It does get weaker. Otherwise, you'd have all sorts of things coming crashing into each other if the greater distance meant a greater force. Fortunately, the universe was not created that way. At least not ours. So it's going to go at the bottom. Now, it is r squared, unlike the potential energy formula, which is just r on the bottom. Notice that there is a space up front that we'll fill in just a moment. Now, why r squared? Or why does it even make sense? If I have a universe with a mass in it, all that's in this universe is this one mass. It's just going to sit there lonely. I stick another mass into it. M1 and M2, I stick another mass into it, and that second mass, what's it gonna do? Now that I have two masses?
Gravitate
Pull
towards.
each other together.
Yeah. So they should get attracted to each other. So here's the question. How does mass 2 know that mass 1 exists? Or and vice versa, how does mass 1 know that mass 2 exists? Mass 1's sitting there fat, dumb, and happy, you stick another mass in there, and it, what, it looks around and sees, oh, there's another mass.
Do they have a gravitational pull? And they like,
Yeah, but
It's taking up
the
space.
gravitational pull, mass 2 shows up, and the gravitational pull suddenly goes, ooh, there's a second mass,
Yeah.
let's do it. That's not what physicists came up with. What they figured is that before mass 2 even shows up, mass 1's given off some vibes. I will call them gravitational pheromones. No one else is gonna call them that except maybe some former students. But it's saying that mass 1 is giving off something. Mass 2 has no idea mass 1 exists. All mass 2 knows is, wait a second, I'm sensing, my spidey sense is tingling here. There's something in that direction.
I know you already said pheromones, but is it like the space it's taking up? Or no?
What it
It's like
senses.
all of a sudden it's like taking up space, you know, in that area. Or no, okay. We'll stick with pheromones.
There- Yes and no.
Okay.
That- Alright, so one idea is it gives us some, generally physicists call it a gravitational field. Because they don't have it, they really don't know what it is. They come up with this idea of, there's this thing that's given off, and they went, got creative, and said this thing that's being given off are called gravitons.